All right. We're going to do two things with the theory, and then we'll get into some of the examples. Last unit, we learned how to do the integral interpreted as area. Okay, so that's what the first box has to do with. We did Riemann sums, where you had a delta x for how wide the rectangles were, and then you found the sum of the rectangle areas here. Okay, see that? Length times width. Now, the area is, okay, you have this little sigma means sum up the areas. When it says the limit as n goes to infinity, that means you're increasing the number of rectangles. So if we show this visually, let's just say that we start at A and we stop at B. Okay, let's see if we can figure out what these statements mean. Now, I have rectangles that are very, very skinny. So I could start with this. Then I could make them skinnier. Right? I could increase the number of rectangles again. So as you increase the number of rectangles, I'm going to increase them again. It looks like you're shading the area. And all I'm doing is creating more and more rectangles in that section. Okay, so we're going to write this statement. We're going to translate it. Okay, this is the theory behind the definition. As the number of rectangles increases to infinity. Infinite number of rectangles. That would be this part of the statement. The number of rectangles increases to infinity. Okay? The sum of the areas, okay, that would be this part. The sum of the areas. Add up all of the rectangular areas. Will equal the definite integral. Okay, look at what's on the other side of that equals. That's the theory behind it. Now there's a lot of algebra steps that we're leaving out between this summation and this integral. Okay? The algebraic steps are not part of the scope of this class, but understanding the idea that an infinite number of rectangles added up actually gives you the exact area, that is part of this class. Now, the last unit, we did that with area and shapes. This unit, we're actually going to do it algebraically, but we're going to start with the definite integral. Okay? So now comes the second part of the theory. Now we're going to write 3 statements and 2 sentences here. And up here in the top right, I'm just going to write down the hierarchy of functions so that I have them for reference. Right, it's the same for every section of notes that we cover. Okay, and this is how we're going to do antiderivatives today. I'm just going to make a note to myself. Antiderivative is going up. Single prime. Okay, first statement. We're going to start with the definite integral, and we're going to figure out how to evaluate it algebraically. A to B, f of x dx. And I am going to bold a certain part of this. Okay, the integral and the dx part, those two things come together. The integral means find the antiderivative. So we're going to write an equals. Well, the antiderivative of little f is capital F. We're not going to put a plus c for the general solution. We're going to put a bar here, or a bracket, a bar or a bracket, and we're going to carry the a and the b over. X equals a, x equals b. Then we're going to write one more equals, and we're going to finish the statement. Now this bar means evaluate. So capital F of b, subtract capital F of a. That is the fundamental theorem of calculus. That's it. This is how you evaluate a definite integral algebraically. You find the antiderivative, you plug in b, you plug in a. Okay, so let's write the statement twice more, but we're going to change up the quantity. So let's put f prime here. Okay, so I'm just going to bold the integral part. And so the integral and dx means find the antiderivative. So I start at f prime, I go backwards to little f of x. Sometimes this looks like a bracket, sometimes it just looks like a bar. Depends on which textbook you open up. X equals A, X equals B. It means the same thing. The bar means evaluate at B and evaluate at A. F of B minus F of A. Notice that you are always evaluating the antiderivative. Notice that the top number goes first and the bottom number goes second. Okay, so let's do the third statement. Let's start at double prime. Go backwards 1. Sometimes you don't see x equals written. Sometimes they just put the numbers there. Although each of them looks slightly different, they do mean to do the same thing. Plug in B, subtract, plug in A. The fundamental theorem of calculus is used to evaluate a definite integral. That's what it's used to do. Notice that there's no picture, there's no area here. It's an algebraic formula to evaluate. Okay, our second sentence is to define a definite integral. Okay, a definite integral has upper, in this case that would be b, and lower, in this case that's a, bounds. There's numbers. The definite integral has a start and a stop place. Okay, so the first box was the reminder about the definite integral being connected to area. The second box here is the new connection to the algebraic formulas. And so the last thing we're going to answer here is, why is there no C value? Last class you had plus C or plus K everywhere. There's no C here. So we're going to look at why. So we're going to write the sentence from number 1, and we're going to work through the steps here. From A to B, f of x dx. Okay. And let's do the antiderivative, capital F of x. But this time, let's put a C, because you're like, that's what you told me to do last class. Put a plus C. Okay, let's keep the bar. Notice that the A is on the bottom, it stays on the bottom. The B is on the top, stays on the top. And plug in. Okay. And so this first box is for plugging in B, and the second grouping is for plugging in A. The top bound always goes first. Upper, then lower. F of B plus C, F of A plus C. That's exactly the 3 things I wrote here, except I put a plus C. Then I plugged in B with a plus C. Then I plugged in A with a plus C. And then I simplify. What combines? Yeah, F of C plus B. So I'm going to distribute my negative, and it turns out the C's cancel out, which would happen every single time. Every time the C would cancel out. Equals F of B minus F of A. And so that's why the formula steps in 1 through 3, that's why there's no C value, because it would cancel out every single time. In the first set I would add C, in the second set I would minus C. So why is there no C value? Because it will always cancel out. Plus C, minus C. Okay, let's go ahead and do the first example, and then we'll make a connection to the calculator. The integral from 1 to 2 of x squared dx. The first step said, do the antiderivative. Okay, there's my antiderivative. Add 1 to the power, divide by the same number. Except this time, there's no plus C. You get the bar, and you get the upper 2 and the lower 1 bounds. Yeah, that was middle step. Last step. Parentheses minus parentheses. The first set of parentheses is for plugging in the upper bound. The second set of parentheses is for plugging in the lower bound. Okay, calculator by hand, doesn't matter. Now this is the value of the definite integral. Remember that definite integrals can be positive or negative. That's sine area. All right, so how does the calculator come into play? Let's hit math. number 9. Type it in, see what you get. 1 to 2 x squared dx. Why not? Is that 7/3? Yeah. So your calculator can check it. But I want to do it also on the graphing screen. Okay. So math number 9 to check it. Great. Let's go to y equals x squared. Okay, that's a parabola. Shade the area it's talking about, right? Definite integrals are connected to area. So what area is this representing? From 1 to 2 under the curve. Okay. Second trace, number 7. Lower 1, upper 2. Yeah, the algebraic formula actually did find the area number. That's what we did today. Okay, so let's do number 2, and then we'll check it in the calculator so you can see the connection. And while I'm here, why not just get the answer before you start? You still have to do the work. You might as well have the answer ready. 0 to 1, 4 plus 3x squared. Okay, 5. So the answer should be 5. Great. Do the steps and see if you can show me the work that gets you there. Okay, see if you can do the steps to get there.
There are reasons why the equation will be used. Right, so it depends. There's a second part of the formula and you don't comment. So depending upon what you're doing, sometimes area is better, sometimes angle is better. It kind of just depends, right? So the lower yeah. Type 1. I don't know. You should, probably. I'll text them.
Okay. So antiderivative. And I'll leave my grouping symbols there. Okay, the first set of parentheses is for plugging in 1. The second set is for plugging in 0. When you take a quiz, I know that you can type it in and get the answer. I will probably say, show me the antiderivative. Then evaluate. Okay? Now, you have a couple choices because I know that these get kind of long with evaluating. If you want to evaluate in the calculator, so I'm going to type in my antiderivative, 4x plus x cubed. Okay? And I'm going to store my values for x. That's fine. I do expect to see the two numbers you're going to subtract. How you get those two numbers, up to you. But I do need to see them. 0 store for x. 0. So we get 5. Okay, so you guys try 3 and 4, and then we'll come back and do 5 and 6 together. Right? Check the answer. You've got your calculator. Find the answer, and then do 3 and 4.
The second one from worksheet 7, because that one's longer, right? And then look at worksheet 8. Same thing. Math 9. So I'm going to type this one. X squared. Comma. 1 comma 2. So the equation and then x and then the lower and then the x. There you go. No, it's fine. No, it doesn't. No, it's fine. So you can take that on. So function, comma, x, that's like the dx part, comma, 0, comma, lower.
Really?
No, I think it's alpha. So this is, I would take my 3/4
And I would write it in front, x squared. Write it in power format, ax squared plus bx. Yes, okay, so we get 6.5. Okay, so I'm going to rewrite this. Don't forget about that. Right, no antiderivative yet. That's 3/4 and then x squared. So I get 1/4 x cubed. There's my antiderivative. How do I know that's the antiderivative? Because I don't have the integral and the dx anymore. I have the bar instead. This part, the integral and the 1 and the 3, are exchanged for the bar and the 1 and the 3. That's how I know I went from the original, right? This piece here, go backwards to the antiderivative. This part is swapped out for that. Now plug in. Okay. So I've got 3 store for x, 1/4 x cubed. Okay. 1 store for x. Yep. 0.25 subtract 6.5. Yeah. Doesn't matter. If it's a repeating decimal, fraction. Not, doesn't matter. No, I don't care how you leave it. Radical form, not radical form, totally up to you. Okay, so I'm just checking the next one, so you guys keep working. Okay, so negative, oops, let's see if we can zoom that up. There we go. Negative point. Keep in mind, right, definite integrals can be positive or negative. That just means that that's probably below the axes. Okay. Antiderivative. 1/4 x4 minus 3x squared. Keep those grouping symbols, 0 and 3. Antiderivative. The integral is exchanged for the bar. Plug in 3, plug in 0. Notice here, I just used the numbers from the calculator, but I showed you both numbers. You should show me both numbers so I can tell that you did evaluate. 1/4, 3 to the 4th, minus. Okay, 7/4, minus 27. Oop. I feel like I did something wrong. Does anyone know what I missed? I missed something. Oh, I know. 3 to the 4th isn't 27. It's 81. There it is. 81/4 minus 27. There it is. Negative 6.75. 1/4, 0 to the 4th, minus. So 0 minus 0, negative 6.75. Guys, see how much work that is? It's okay if you just use your calculator and you plug it in like that. I just need to see both numbers, and I need to see the antiderivative. All right. 4 more. Let's look at number 5, which takes a little bit of rewriting first. Question, Alex? Okay, see this third part here? Before I do my antiderivative, I have to put it in the power format. That x squared, it has to come up. Okay, antiderivative. And I know that I'm going to get to the antiderivative when I exchange the integral and the dx for the bar. Okay. Up the power, reciprocal. Up the power. Okay, add 1 to the power. Divide by the same number. Now you could evaluate like this. I think I'm going to do one more thing before I plug in. I'm just going to put my x back on the bottom. It's a little bit easier to plug in this way. Yeah.
What are you putting again?
Math 9. Okay, this minus this. Top number, bottom number. So if you do it this way, try the f of 1. Try plugging in 1 to this. You're going to get negative. Yeah, it is 0. Yeah, it is 0.
Wait, do you have to do it through the calculator?
No, it's just to check.
Okay.
Right? It's just to check. Okay, so... Okay, let's see what I can do. 2 store for x. Okay. 2 store for x. So I'm going to try it. So I'll put in the different pieces. 1 over 2 x power 4 minus 3x squared minus 3 over x. So I get negative 5.5. Now I'm going to try the 1 store for x. Notice I'm not actually writing the plugging into here because it's really tedious to write that the longer the function gets, but I am recording the number. Oh, that ends up being 0. You do end up getting 0 on this one. Could happen. Negative 6. 0.
What am I doing? What am I doing? No, it's supposed to be.
Oh, okay, so hold on. Okay, so you either type this in exactly how you see it. This is the antiderivative. You don't type the antiderivative in the input. Okay? You're like mixing. You're putting this statement in here. You're mixing different lines. If you want to evaluate in the calculator, you type it exactly how you see it. Right? Exactly how you see it. If you're going to do it the antiderivative way, that's the by hand way. You do the antiderivatives, plug into, subtract, plug in 1. All right, let's look at number 6. Now, see that divide bar? See how this divide bar is longer than this divide bar? This one, the 3 was divided by x squared. Here, all 3 pieces are divided by t squared. Now, I'm going to write mine like this. And I'm going to distribute t to the negative 2, which is the same thing as dividing everything by t squared. And then I'm going to distribute this. So I end up with 2 plus t to the 1/2, because the t squared part gets t to the 0, okay, minus t to the negative 2. But I haven't done the antiderivative yet. All I did is I rewrote that into a power format. Now I do. Right there's a little line. Now I do antiderivative. Add 1, reciprocal for fraction. Add 1, reciprocal. And I notice I see a minus minus there, so I'm going to just rewrite that. 2t plus 2/3 t to the 3/2. I'm just going to say plus 1 over t. Get my grouping symbols, write my bar, and my 1 and my 9. Right here, the minus minus is the plus. The t to the negative 1. Okay, so are you okay with this part right here? Okay, add 1 to the power. Divide by the same number. No? Okay, I'll come show you. That's what it comes down to. Does not matter which format you use. So, okay, so reading the question, it says find area. First thing I know about area is that it's always positive, which means my answer should be a positive number. And because they're asking about area, I want to draw the picture to make sure I'm going to interpret it correctly. And so I'm just going to list a couple points here. And I have this parabola. I have x equals 1 and x equals 2. Okay, so here's 1 and here's 2. I'm going to go ahead and type this equation in. So 6 plus x minus x squared. Okay, and graph. Okay, so it's an upside down parabola. And I'm going to list just a few points in this section here in order to graph it. It doesn't have to be perfect. I just want to have a general idea of what area the question is referencing. So I'm going to go to my table and jot down a few points here. So -1, 4, 0, 6, 1, 6, 2, 4, 3, 0. Okay. 1, 2, 3, 4, 5, 6. And graph, so it looks like this, right? I can kind of see the symmetry. Okay. And I'm going to include the x-axis here. So find the area bordered by the curve. The lines x equals 1 and x equals 2, so it gave me the start and the stop point. And the x-axis. Okay, that's down here. So I'm going to shade the region that it's talking about. Okay, that's it. That's the region. Now it's asking for area. I know, right? This is where that first box comes in. The definite integral can be interpreted as area. And it says, write the definite integral that can be used to find that area. From 1 to 2. Start at 1, stop at 2. The area under the curve. 6 plus x. This definite integral will actually find that area. That's the connection. When we first started this, I gave you pictures, and then we wrote the integral. Now you kind of have to find the picture and the integral. So we're adding one step to it. Evaluate using the fundamental theorem. That means by hand. That's what the fundamental theorem means. Like, do the antiderivative and plug it in. positive number. Okay. Making sure that what I found did represent that area. Um, 8 1/6? Yeah, 8 1/6. Or 49/6. It doesn't matter which way you write the number, guys. Decimal is fine. Okay, see if you can draw the second picture that's being described here. Okay, once you finish the first one, try the second one.
Stop. No. I'm doing that.
Now see if you can get the picture for example B. Am I silly? What did I do?
I got 5.1.
Yeah. I did the same thing earlier. It's 6. It's 6. So it's 5. Yeah, you're right. No, you're right. I did it correct once and then wrong twice. Good call. So it's 5 1/6 or 31/6. Is that better? Thank you. Yeah, thank you. All right, let's look at the next picture. Make sure you catch the error. I added something wrong. It should have been a 6.16 here. For some reason I had 3, so should be 5. Should be a 5. There we go. Okay, so let's evaluate. So -2 to 1, -2 to 1. So I'm going to graph maybe a few extra points. Okay, and sketch the picture. -3x squared minus 2. -2, -14, -1, 0, 1. Okay. 1, 2, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, 2, 14. Here. 1, 2, 3. Okay, so there's my sketch of the parabola. X equals -2 is right here. X equals +1 is here. The x-axis is here. And shade the region. Okay, well, I know that area is positive. It says find the area. Well, whatever I'm going to label as area of that region better be a positive number because area is always positive. The definite integral, however, could be positive or negative because it takes into account sign and direction. So I am going to write the definite integral from -2 to 1. And I know that if I do this, that it would be negative, just based on the diagram. Forwards and down would be a negative number. So what can I do to adjust this statement that's going to make sure that I get a positive answer? Yep, you could put absolute value bars around it. You could put a negative in front of it because you know visually by looking at this statement, this integral is going to give me a negative number, right and down. But you're like, area has to be positive. So a negative sign would work. An absolute value sign would work. Okay, so now let's evaluate. I'm going to leave that negative out, and I'm just going to worry about my integral. Antiderivative I'm gonna do the negative last. Plug in 1. So we get -3. So the area is positive 15. No. The area is 15. The definite integral is negative. The area is 15. The definite integral would be negative. Okay, when we did this last unit, we always labeled the graphs with different area numbers. And then we evaluated definite integrals where we took into account the direction. Here it's like a little backwards. I have to look at my definite integral and be like, okay, well there's some direction implied here, but the area of that section is positive. Okay. The last example should be x cubed from -1 to +1. So if you can go ahead and change that. And then see what you come up with for that section. Statement to evaluate the positive 15. So think of it this way. Let's just do this. Just leave it. And then when you write area, write positive 15. That definite integral that I wrote represents the shaded region, which is obviously going to be negative forward and down. But if I want to label it with area, I need to label it with a positive number. Almost. Okay, yes, but draw the picture for this one. Because none of your algebra graphs. Yeah, that's just an thing. Okay, try that last one. Get a picture and see what you think it represents. You can do it. I get this. This makes sense. Good. Draw the picture. No, your algebra is not wrong. Draw the picture. Okay? Why? Is our last Okay, can you do this instead?
I guess use them first, right?
You gotta do this before you do that. Gonna draw the picture. X, Y. Okay, here's my diagram. Looks like this. Oh, there's kind of two sections here. X cubed between -1 and +1 and the x-axis. Okay? If I write my definite integral, it kind of looks symmetric. And so I'm going to do the left section. Didn't we split area up in that one unit where you did each section separately when they had different directions? So this is right and down. This one is right and up. Hold on. Isn't 0 connected to? Think of your properties. Now I know that this first section would be negative just because I can see it on my graph. Now I'm asking about area, and so I'm going to use my knowledge of definite integrals in order to interpret the area. Okay, 1/4 x to the 4th. And I'm going to kind of re-sketch my picture here. I think I'm going to zoom it in. Okay. -1. I'm just zooming in here. If you were to label that graph with area numbers, you would get +1/4 in that section. Yeah. Did your definite integral evaluate to be negative? Yes, because that was right and down. But the area of that section is +1/4. So now I'm going to do the other section. The area of the second section is also 1/4, which means that combined, the area is 1/2. So when it asks for area, you have to look at the picture and make sure that you divide it up appropriately. Right, two different sections here. -1 to 0. Zero to 1. Two different sections. The orange integral came out to be negative because it was right and down. The pink one came out to be positive because it was right end up.